Welcome back. In this video, I'm going to discuss unique pointers as formal parameters. To get started, I plan to include the memory file for smart pointers, and then I have this abstract entity class for the examples in this video. As in some of the previous videos, it has a constructor with a default argument of 44 right here for the member parameter, and I'm going to set the member, which has an integer member in the private section right here. I'm going to assign the member parameter to that. In the destructor, it's simply going to print out entity destructor invoked. And then I also have a void toString function which is going to print out the member. Next, to demonstrate unique pointers as function formal parameters, I have this print function, write some display or print function, and to start off with I have this uptrp for unique pointer parameter, and that is of type unique pointer, and I pass an entity. In the first demonstration we will pass by value to see how that works, and in the body of this print function I'm simply going to do a check. I'm going to check is the unique pointer parameter not equal to null pointer. If so, do unique pointer parameter toString, otherwise print out a null pointer. Okay, in main I construct a uEntity pointer, which is of this type, unique pointer, and I pass an entity, of course. Now for purposes of this demonstration I'm going to be explicit, but of course you can have auto here as well for the type deduction, and I'm going to use make unique, pass in entity, and pass in 55 for the constructor. Now if I try and invoke the print function and I pass in uEntity pointer as an argument, then we will get an error. Remember that in the print function currently we are passing by value. Okay, when we try and do that, it's going to construct uPointer parameter by using the copy constructor, but as we've seen before, the copy constructor is deleted for the unique pointer. So what we have to do is we have to move this resource. Well, in other words, in this example we have to move the heap object that the uEntity pointer manages to the uPointer parameter. So how can we do that? Well, we're going to use the move function like that. I'll add this extra if statement in here. It's going to check whether uEntity pointer is a null pointer, and then it's going to print that out, which should happen in this case because we have moved, basically using move semantics, we have moved the heap object that is managed by uEntity pointer over to this uPointer parameter. So following the print function invocation, the pointer that the uEntity pointer manages should be null pointer. Build around that. And you can see this works fine. It's going to invoke that function, the print function, and it's going to print out 55. When program execution reaches the closing brace of the print function, it's going to destroy. Right when it reaches the closing brace, it's going to destroy the uPointer parameter, which is a parameter that is local to the print function. And of course with this move function, we are going to move the ownership or the management of that heap object over to this uPointer parameter. And so when uPointer parameter goes out of scope, it has to deallocate that heap object. And we can see that here entity destructor invoked. Then program execution returns to main, and of course this entity destructor is invoked now, and uEntity pointer is going to be null pointer. Because the managed pointer of uEntity pointer is null pointer, we will get the statement printed out, and then end of program as we would expect, and that's what we get. Next I'll discuss how we can do pass by reference, but before I get to that, I want to show you that we can create references to unique pointers. I'll create this unique pointer reference. This is going to be a reference to unique pointer. That is basically now going to be an alias for uEntity pointer. Build around that and you'll see that works fine. It prints out 55 twice. That is because we do the toString right here and then we also do the print function. So with this I've demonstrated that we can create a reference to a unique pointer, and I'll just delete those two statements and then I'll go back to the print function, and then in the parentheses for this formal parameter, I'll change this unique pointer parameter to a reference to a unique pointer. And then in the main function I don't have to move anymore. Now when we invoke the print function and we pass in uEntity pointer as an argument, this unique pointer parameter is going to be a reference to that. Well, in other words, it's basically going to be an alias for uEntity pointer. Build around that invokes the print function, it prints out 55, and then it's going to return to the main function, it's going to print out end of program, and of course we get the entity destructor invoked as well. In this instance, just to reiterate, when we invoke the print function, the unique pointer parameter is going to be an alias for the uEntity pointer, and When program execution reaches the closing curly brace, it's not going to destroy or deallocate uEntity pointer, it's simply going to destroy the alias or the reference, and of course that does not invoke the destructor. The destructor is going to get invoked on the object itself, uEntity pointer. That is when we reach the closing curly brace of main. That being said, we do need to be careful when we have references to unique pointers, that is as formal parameters, because I can modify the state of the unique pointer. This is not a reference to unique pointer constant, so I can modify the state. I do unique pointer parameter.reset, which as we've seen before is going to deallocate the object on the heap that the unique pointer manages, and since the unique pointer parameter in this example is now an alias of uEntity pointer, that means this statement right here is going to deallocate the heap object that the uEntity pointer manages. Alright, let's just build and run that. From this you can see what I mean. It's going to print out 55, then we get entity destructor invoked. That is because we invoke the reset member function, so it's going to deallocate that object on the heap. Program execution returns to main where uEntity pointer is now going to be null pointer, and then we get end of program. If I move this line up, if I move the statement up where we invoke the reset member function, then of course it's not even going to do this toString function, it's simply going to print out null pointer. Okay, so build and run that. We get entity destructor invoked because we invoke that reset member function, then we get a null pointer. Then back in main is going to print out uEntity pointer is null pointer as well. That brings me to passing by reference to unique pointer constant. Now of course the parameter is still an alias for whatever we pass in here, so in this case uEntity pointer, but we cannot modify the state of the unique pointer within the function body now, so this will be an error. If I Ctrl B to build, we will get an error. And as with other structs and classes, this may be the best option, passing by reference to constant. I'll just comment the statement out here, and now we can build and run, and this will work fine. As we can see, it will not print out uEntity pointer is null pointer because the statement in main is going to fail. And that is because we no longer call the reset member function in the print function. I would like to note that if we pass by reference to unique pointer constant, we cannot change the state of the smart pointer as we've seen, but you can change the state of the heap object that the smart pointer manages. For example, if I go back to the definition of the entity class and I go and create a setter, okay, create a simple setter, set member, and it's going to take in an integer, and it's going to set the member to the member parameter, or in other words to the argument that we pass in, back in the print function. I can do this statement without getting an error. I do the unique pointer parameter, the arrow operator set member 150, and let's just build and run that. And we see that prints out 150 now. So again, we cannot change the state of the smart pointer, but you can change the state of the heap object that it manages. A summary on unique pointers as formal parameters. We can pass by value, but that is going to require the std move function on function invocation. Now of course move is going to be implicit with a literal, or in other words an R value. Note the simple example prototypes that I have for each one of these. We can also pass by reference to a unique pointer, in which case we can change the state of the smart pointer and or the state of the heap object that it manages. We can also pass by reference to const. Now in this case we cannot change the state of the smart pointer, but you can change the state of the heap object that it manages. Okay, we've discussed passing by value, passing by reference to unique pointer, and also passing by reference to unique pointer constant. Now as an exercise, I'd like you to reflect on R value references, and what do you think is going to happen when we pass a temporary unique pointer entity to the print function as an argument? Can we even do that, and how would you go about doing that? Next, I'd like you to modify the print function from the previous example so that it accepts an R value reference to unique pointer entity. Once you've made that modification, I'd like you to think about what arguments we can pass into the function. Alright, go ahead, pause the video, try this exercise, and when I come back, I'll show you a few things in Visual Studio. I've made some slight changes in the main function. For example, I've changed the name right here of the unique pointer to up, so up_entity. I'm just demonstrating this here because it really depends on the convention that you want to go for. In CRUNZN, for example, the convention with pointers and with smart pointers is to do p_entity, for example. So p_ and then the raw pointer or the smart pointer name. Now for this demonstration, just to differentiate between the unique pointer and a raw pointer, and also later on we'll do shared pointers. For that reason, I've done entity here, and I've prefixed that with the up underscore for unique pointer, right? So again, it depends on what you want to do. And of course, if you use Qt, Unreal Engine or CryEngine, for example, then make sure to look at the appropriate C++ conventions. Okay, getting back to the print function now, let's say we want to pass in a temporary. How can we do that? Well, I'll just comment out that and I'll remove this line here. Actually, we won't be using this for right now. What I'll do is, let's say we want to create a temporary object here. We can use make unique. Okay, I'll use this dirty make unique function and I'll pass an entity for the type of the object that this is going to manage. And then I'll pass in 55 for the construction of that heap object. So this expression right here is going to return a unique pointer which is going to manage an entity on the heap. So of course this function is going to return a temporary object, and then we pass that in to this print function. Currently the formal parameter is a reference to unique pointer entity constant. Okay, and I'll just remove these unnecessary lines here left over from the previous example. So if that unique pointer parameter is not null pointer, then I'll do unique pointer parameter toString. Build around that is going to print out 55 in the print function. You'll notice that I do not use the move function within this print function invocation. Now of course, if you take away the cons here, again reflecting on R values, this is an R value that is going to return again. You may remember when we pass by reference, in other words to a non-const, then the argument must be an L value. Alright, so let's just go and change this here to an R value reference now. We do 2 ampersands if you remember for the R value reference, and then the red squiggly will go away because this is perfectly acceptable. This is an R value, and of course an R value reference will accept an R value. Pull around that and you see that works fine. It prints out 55. The entity destructor gets invoked and everything works fine. Also, you may not do this, but I just thought I'd demonstrate that here out of interest. So I'll go and select this up entity. And if I want to pass that in here, of course, up entity is an L value, so I have to convert that somehow to an R value. How do we do that? I have demonstrated with the old C style cast, but in this case, I'll use static cast. Now, I have to think for a second, what exactly do we want to cast to? Well, for the unique pointer to work with the print function now, since it has as a formal parameter an R value reference, we have to convert that to a temporary. So I have discussed this in a previous lecture, but of course the syntax is a bit more complicated now. So we have this unique pointer entity, and we pass in these 2 ampersands here as well. Pull and run, and this will work fine. Now we get 55 printed out, then end of program, and then we get entity destructor invoked. So that is actually going to be following the print function invocation. But of course we can still use the move function. So what I'll do is, I'll use that std move function, and if I build and run now, you can see that works too. I'll just change that back to a reference to a unique pointer instead of an R value reference. And now we'll get an error if we try and do move in this print function right here. Reference to a non-const must be an L value. So again, we can think of this move function as returning an R value. Let's go and change the formal parameter of the print function to a reference to unique pointer constant. And now this invocation will be fine. Okay, I can build around that and that will work fine. As you can see, it prints out fine. Destructor, it gets invoked. That is going to wrap up this lecture. In the next lecture, we'll talk about returning unique pointers from functions.